This is physics graphing, and this is the 0.3 notes. Taking a look, when we talk about physics and graphing, we do have a few general rules. First one, you must always have a title. If you do not have a title, you will lose marks. The easiest is just whatever you have on the y-axis versus whatever you have on the x-axis. So if this is distance and this is time, the easiest thing to call this is distance versus time. Just y-axis versus the x-axis. Make sure you use half the graphing area at least. Don't just make a tiny little graph that goes like this. Make sure you're using most of the graphing area. And the easiest way to do that is make sure that the y-axis covers at least 75% of the data values, and the x-axis also at least 75%. Now, keep in mind this is not a connect the dots, so if the trend line looks like this, we use a line of best fit or a curve of best fit, not just connecting the dots in some sort of rearranged way. Now, if it's linear, it's best to use a ruler through there and make sure you're drawing a straight line. Now, because you could lose your points, what you're going to do is you're going to circle each of those before you put your line of best fit, and that just helps you to find them later. Okay. The x-axis is always your manipulated variable. That is a variable that we cause the change in. It is the relationship being studied. We would call this the input. Time is almost always the x because we choose what time to make the measurement. So the x-axis, this is your manipulated. The y-axis is your responding variable. So we put the responding variable on the y-axis. So taking a look at the title, it's always the responding versus the manipulated. Sometimes that y-axis is also called the output. Each axis should be labeled as follows. The variable represented on the axis. Okay, so we need to say, what is it? Proper units for each variable. And a scale which has even divisions. Okay, so as we're putting this together, if we've got time on the x-axis, we put seconds. 1, 2, 3, 4, 5. These should be even. 1, 2, 3, 4, 5. Now you don't even need to label each one, but it should be even. We're not going to have it look something like this. 1, 6, 7, 9, 15, right? Those are uneven. Don't do that. Do it like that. And again, if you want to go like this, you could go 2, 4, and skip each one 2. That's fine. Labeling units, but make sure that they are even. Now, two types of graphs. The first one we have is a straight line, which is the most useful, and that is what we call a linear graph, right? It allows at one glance to tell how the experimental data points fit the predicted behavior, right? And so we take a look here, we've got distance versus time, and so we're just constantly moving same distance over the same unit of time. Call that a linear graph. An exponential will always show an increasing relationship, right? As x increases, y increases more and more and more, right? We go to the first 100 and it increased that much. The second 100 increased more. The third 100 increased more. The fourth 100 increased even more. We see an increase in that growth each and every single time. So as x increases, y increases more and more. We also have a couple of inverse relationships. The y is equal to 1 over x and the y is equal to 1 over x squared. Both graphs will look something like this, where they will show in constant decreasing in that shape where it's getting lower and lower and lower each time, right? So in order to figure out what type of relationship we have with some raw data, meaning we don't know if it is an x squared, x, 1 over x squared, 1 over x, or even if it is just linear, right? What we're going to do is we're going to calculate the change data in a new axis column of data and then graph new numbers. So what we're doing is we're saying, okay, well, if y is equal to x doesn't work, well then let's try y versus 1 over x, or y versus 1 over x squared. And we calculate these values, plug them in, and see which one generates a line. So we take a look at this example here. We've got a responding variable here, we've got a manipulated variable, and the plots the data, we've got A and B's, and the data points here show one of these inverse relationships. Now, we don't know if this is 1 over x or 1 over x squared. We don't know if that is the relationship. So we're going to just balance out and try to figure out which one it is. So we've got A here, B here. Now remember, this is on the y-axis, this is on the x-axis. So 1 over x would represent 1 over A. And we just plug those values in. 1 over x squared, and we evaluate and just put them in those data. And so we're going to make two new graphs. One where it's the y over 1 over A, and one where it's the y. And I say y, it's the unit b or y. B versus 1 over x squared. And so with this graph, the graph we'll call Q, right, will be a case of where we'll take this set of data and this set of data for Q. And for this one, which we'll call R, graph R, we'll have this set of data and this set of data to plot the points. Again, looking for which one winds up generating a linear graph. Now, if we try 1 over A squared, or 1 over A, sorry, we actually get data that looks like this. And that's just plotting those data points that we did from the last slide. Right? That is what graph Q looks like. When we try A squared, this is what graph R looks like. And so, given these two, what we can figure out is that the relationship is basically y is equal to 1 over x relationship. Now, y, we know is the value of b. 1 over x is 1 over a. And the relationship has a slope, and so we'll put that there, which will have the slope. And we don't have any y-intercept because the y-intercept is just 0. The slope always represents whatever we've got on the y-axis over whatever we have on the x-axis. So in this one, this graph, which should have a title, distance versus time, the slope represents distance over time. And distance over time is the same as speed. So the slope of this line would represent the speed. Now, this graph is going up 9 feet over a time of 6 seconds. And so it's traveling at 1.5 feet per second. Okay, and we know that because that is a slope. The change in the y-axis, right, going from 0 to 9, that's our change in the y over our change in the x. Areas underlined always represent the y value times the x value, and in each of these cases we've got velocity multiplied by time. If we take the velocity multiplied by the time, that is actually equal to the displacement. And so in each of these, if we calculate the area, in this case, 15 times 4, in this case it's 15 times 6 divided by 2, and here we've got 15 times 4 divided by 2, or 60 meters. This one is 30 meters, and 75, so that would be 45 meters. All right, so let's take a look at a few graphing examples. Okay, and the first one we're told that eyes are manipulated to measure the effects of H, right? So eyes here, and so this is our manipulated variable. And because it's a thing we're changing, we're going to put that on the x-axis. H is the responding. So we're going to put this on the y-axis. And the data is given here. We're asked to draw the graph, find the slope, and give a mathematical expression. Now, the mathematical expression, generally speaking, is going to be y is equal to mx plus b. And we're going to find the slope. We'll find the y-intercept. Y and x will be in there, and we'll plug that in. Okay, so I know this is on your sheet. It's going to come out of the screen, but we're going to put that graph right there. Okay, and it's going to have everything we need. So just remembering those data points. First of all, again, we're putting H, which is measured in GDs, on our y-axis, and I's, which are measured in JDs, is going to be on our x-axis. Now the I data actually goes from 0 to 75, but we've actually only got 33 squares here. So we're going to need to take 75 and divide it amongst 33, and we have 5 data points, each one separated by 15. So probably going, let's say, if we call this 0, 1, 2, 3, 4, 5, we will call that 15, 1, 2, 3, 4, 5. We'll call that 30, 1, 2, 3, 4, 5. We'll call that 45, 1, 2, 3, 4, 5. We'll call that 60, and 1, 2, 3, 4, 5. We'll call that 75. Now, we probably could have got away with 6 between each one just to spread it out a little bit, but that is at least 75%, so we're pretty good there. Taking a look at the GDs go from, are a little bit trickier. They go from 0.45 to 0.62, and there's 23 data points here. So if we say 20 data points, it brings us to the 0.6. So we've got 23 points here. So if we say, let's say, every 4 is equal to a 0.1. I think that should be good enough. I actually think we might run out of time. 4, 8, 12, 12. Yeah, we're going to run out of space. So maybe we'll make that every 3. 0.1, 2, 3, 0.2, 1, 2, 3, 0.3, 0.4, 0.5, 1, 2, 3, 0.6. Now, the graph again is always y versus h, so this will be h versus I. Now we're going to plot our points. Our first point is 15 and 45, which 15 and up to 45 would be right around here, and we circle it. 30 and 0.49, which would be just below the 0.5, and we circle it. 45 and 0.54. Now, that's a 0.33, so it'll be somewhere around there. 60 and 0.57. Oh, shoot, I was a little bit off with that last one. 60 and 0.57, be somewhere around here. And the last one, 75 and 0.62, which would be somewhere around here. Now, using a ruler, we're going to draw a straight line through there. So I'm going to get a shape of a line, putting it in place, and seeing if we can't move this around to get it to line up through the data points. So it'll look something like that. That's our graph. Now in order to, so that's part A. Part B is to find the slope. We're going to pick 2 points that are not data points, and I'm going to choose this one and this one. The wider we make this, the more success we're going to have because it will average out any errors that we've made. But we're going to need to find the delta y and the delta x. So that change in y is going from 0.433 up to 0.633. So that would be a delta y of 0.2 change, right? You may remember this from y2 minus y1. It's a change in y. Here, we're going from a value of 9, 75, to a value of 81. And so your delta x, the difference between those two, is 72. And so your slope, which is your change in y over your change in x, your change in y is 0.2 over 72. And when you calculate that, you get a value of 0.00277. And that 77 is repeating. So lastly, if you want to get the mathematical relationship, it's going to be y, which is h, the slope, 0.00277, what we have on the x-axis, plus the y-intercept. And so, on back a little far here, the y-intercept seems to be hitting somewhere in the neighborhood of 0.4. So we'll go plus 0.4. And that is your mathematical relationship. Let's take a look at our second example. And here we've got the gravitational force between two objects is measured at various distances, and the results are below. So because they're measured at various distances, this is our manipulate. This is what we measured. This is what's on our x-axis. Sorry, this is what we've determined. We've measured the force, and so that is our responding, and so that will be on your y-axis. We're asked to draw the graph with this data, and then we're asked to linearize it. And what that means is we're going to try different things, either an x squared in this column, or a 1 over x, or a 1 over x squared, and see which one works. Right? Once we've linearized the data, we'll find the slope of the linearized graph and give a mathematical relationship, similar to what we did above. So first thing we're going to do here is we're going to need to linearize, graph this data. Sorry, I've moved ahead. And our graph paper here is the same. We've got our force, which is in newtons here. We've got our distance measured in meters here. And so if we call that 0, we'll call every 5 5s. We can call each one and that works out nicely. Each square is just equal to 1. The x-axis is a little bit trickier. We're going up to 0.064, and so each 3 of these I'm going to call 0.01. Zero 0.04, 0.05, 0.06. And that should be good. Plotting our points, we know at 5 meters it was 0.64. So that's 0.0633, so just a little bit above, and we'll put that in. At 10, it was sitting at 0.16, and so already you can see it's kind of a sharp drop, somewhere about there. 15 is 0.007, so somewhere about here. 20 is 0.04, somewhere about here. And 25 is at 0.3, somewhere about here. So again, we can't actually use a ruler with that. And so we're going to try to draw a smooth curve as best we can. Now, this graph is obviously not linearized, but it is showing an inverse relationship. So it's either 1 over x or 1 over x squared. It's not the x squared because an x squared would be constantly rising, and it's not doing that. It's constantly falling. So we're going to need to graph this with the next data. We're going to, first of all, let's try, instead of 1 over x, we'll try 1 over d, which 1 over d is 1/5 or 0.2, 1/10, which will be 0.1, and we'll keep on going. 1 over 15 is 0.06 repeating. 1 divided by 20 divided by 20 is 0.05, and 1 over 25 is 0.04. So this is what we're going to be putting in for the data points on the x-axis. Right? This is still our y-axis. Okay, so the y-axis remains the same. And force measured in newtons. The x-axis is going to be 1 over d. And I feel like I'm a little bit off screen here, so I will move down. Try that again. 1 over d, which would be 1 per meters. Now, as we've done before, the y-axis remains unchanged. The x-axis, however, has changed considerably. It's only going up to 0.2, so we're going to pick, let's say, 20 squares. 1, 2, 3, 4, 5, 6, 7. Wait, sorry. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14. And we'll call this 0.2. So this would be 0.05, 0.1, 0.15, and 0.2. Now, 0.2 is at a distance of 0.64, which would be somewhere right about here. The next point is at 0.1 and 0.16, which would be somewhere around here. The next point is at 0.66, which would be somewhere around here, and 0.07, looking like that. 0.5 and 0.4, looking like that, and 0.04 and 0.3 looks something like that. And what we see here is we've got sort of a trend, but it's kind of bending upwards. The trend looks more like this. And if we were to put a line in there, shape line, right, we see it's quite off base. The line's not going to work. So we'll undo that. Right. So the 1 over x approach does not work. And so we're probably looking at an inverse square relationship. So we're going to do this one last time. This time 1 over d squared is going to go in here. So 1 divided by 5 squared, 1 divided by 5 squared would be 1 over 25, or 0.04. Now I'm going to add a couple of zeros there, and you'll see why here in a moment. 1 divided by 10 squared is 0.0100. 1 divided by 15 squared is 0.0044. 1 divided by 20 squared is 0.0025. And 1 divided by 25 is 0.0016. Now, I've done that because the last 3 digits are all consistently. We can say we're kind of going basically from 0 to 400, starting at the hundredths position. And so that is again going on our x-axis. This is going on our y-axis, and the y-axis is again going to remain unchanged. So as we graph this, we're going to have y, which is force versus 1 over d squared. Force here remains in newtons and will be unchanged. 1 over d squared will be here, and that's per meters squared. So I've just quickly added that in, and on the bottom here, we're going to make and we'll go every 8 to be 0.01. 0.02, 0.03, 0.04. And so that first point being at 0.064 and 400 would be somewhere about here. The next point at 0.1, so it's all the way over here, is at 0.16, which would be somewhere around here. 0.004, so about here, and that sits at 0.07, be somewhere around here. We've got 0.0025 and 0.4, which would be somewhere around here. And lastly, we've got 0.0016 and 0.03. That would be somewhere in the neighborhood of here. And we can see we've got a fairly linear set of data. And just get that into position there, and that becomes our linearized data. So now that we've got our linearized data, we can find the slope. Again, finding points, I'm going to choose this point and this point. Again, we're looking for points that are not on the graph. Okay, and we're going to look for our delta y and our delta x. Y spans this spot, x spans this spot. Y, we've got 0.0125 all the way to 0.035. Y, we're going from 0.02 all the way to 0.0566. So the slope being delta y over delta x means that that change in the y is going to be 0.0366 over x, which is 0.0225, and 0.0366 divided by 0.0225. That gets you approximately a slope of 1.63. So as we're putting this together to find that mathematical relationships, that's y is equal to mx plus b, which in this case is 0. Now you could simplify that to say 1.63 over d squared. Okay, I hope that helps. If you have any questions, let me know.